All right. So, what did you guys think about? So let's talk about 4A. Obviously, this is in terms of pre-calculus and high school students, this is a less common, if at all, way of graphing a function parametrically. So what advantage might there be to having students graph parametrically over our traditional y equals f of x? What did you guys think about? Yeah?
I want to show the relationship between the variables.
Okay.
Or like, because a lot of students don't know what f of x is, like the input and the output stuff.
Okay.
And this way, if they learn it this way, you can see how they vary together. And like more explicitly, like they need a deeper understanding to be able to graph parametrically.
So you touched on understanding what f of x is.
Yeah.
How does this help understand what f of x is more?
Like x is obviously that your input, and then the y is your output. So like it kind of shows. Well, I don't know. For me, it seems like it breaks it apart more, and they might be able to understand it more.
Okay. Other Tyler.
I liked how it kind of got it into these are a set of points, and so you get students away from thinking, well, this is the line that it gave me, and
Okay.
well, this is the collection of points that it's defined as.
Okay.
So they're no longer thinking, oh, well, this is what it looks like. This is the graph. No, it's every single one of these points give us what this shape is.
Okay, so there's more of an emphasis on points. Cool. What else? What did you think about this question? What might be an advantage graphing? Yeah, Alex.
Well, kind of extending off that is that with the points thing, it's like students can no longer just y equals f of x. They can just plug it into their graphing calculator and then find specific points without having to really think about like where they are or how they, or maybe precisely how the function works in such a way as to provide those points. But if they have to constantly redefine it to get the points they want, say they're looking for a specific output, then that's going to force them to kind of understand function notation maybe a little better.
Okay. Cool. Other comments?
I also think that sometimes not all of the graph is needed. So this type of interval, that you can capture an interval,
Okay.
is very helpful so that you can kind of look at specific portions of figures or graphs.
So is that something that you can do parametrically, but not with y equals f of x? Capturing an interval?
I think it's a little easier.
Okay.
You can set up intervals, but this was so much easier to have like the slider bar be interacting with it. So that you could just multiply by n or t to change things up in certain areas.
Okay. Other possible advantages? Yeah, sorry.
Well, I answered the question after doing the solving problems.
Okay.
So, when I came back to it, I had I think a better understanding of the questions I had finished beforehand
Okay.
than I would have had before. I had a better understanding of what each part did, specifically independently of each other and working together. So if I would change one thing, I could see exactly what changed and how my graph was affected.
When you changed one thing, what did you?
Change like one parameter, like change the t value or change the n value, or even changing the 2 pi or to 4 pi or something like that. At least I got a better understanding of how every part worked.
Okay. What is the emphasis? So the traditional way. Okay, what is the emphasis of this? When we think about defining or graphing a function y equals f of x, where's the emphasis? That's maybe not so much in parametric equations. Crystal? No, just thinking about graphing this way. Thinking about this framework for graphing. Yeah, Fredo.
It's more focused on the output.
Okay.
Actual graph. And whereas in a parametric, you have to deal more with what the input is, so you get whatever it is you're trying to see.
Yeah, so this is like focused on the output of the function. It's focused on the y value in the graph, which is okay because sometimes that's where we want the emphasis. But do you see how that's taken away in this? So here you have equal emphasis. You have your x coordinate and your y coordinate. So as I've listened to some of what the comments that you've said, let's talk about what this construct of the graph. What is the input? What is the input? T is the input, right? Okay. And what is the output?
X and Y.
What did you say, Michael?
I said X and Y.
X and Y. He said X and Y. Is that the output? Or is f of t the output? Ordered pairs is the output, right? The input is t, the output is an ordered pair, right? So that puts an equal emphasis on your x coordinate and your y coordinate, where your output here is just the output of the function. So it's just this emphasis on that output quantity or the y value on the graph. Okay? Other comments about the differences between graphing one way or the other? Okay, so let's take a look at this one here. I wish I could copy and paste that, but so what was it? Okay. And so, do we have it, if I just wanted to graph it in the traditional way, first of all, will this line graph the function?
No.
How is it using x in this command line? How is graphing calculator seeing x in this command? Is it seeing it as the x-axis? No, it's just seeing it. How can you define how it's seeing it? Dummy variable, placeholder, right? So this is the one case when you define a function, if you use x, this is the one time when it doesn't see x as the x-axis. Any other time, so now if we want to graph it, what do we do? What about this x? What about that x? Now it sees that as the x-axis, okay? It's going to plug in all x values according to the rule and spit out all the y values and graph all the points, right? So can we do this on a bounds of -2 to 3 this way? Yeah, we've done this, right? We've done this. So what would we do, Michael, comma?
-3 is less than or equal to X.
It's negative
-2.
Oh, sorry. -2. Less than or equal to X. Less than or equal to 3.
Yeah, we've done this, right? So everyone should have thought, of course you can do this. You just define which x values you want to graph it for, and that's what we get. So your task was to do it parametrically, and of course, so now we can do Control 2. Control 2 again. And so I have to type this whole thing in again, right? Dang it. Oh, I don't have to type this whole thing in again? Oh, cool. I'm glad you guys knew that. All right, and so if I graph that, so let's turn this one off. What'd you say? So the graph is what is the graph showing us? Yeah.
All the points from t equals 0 to t equals 1.
Where do you see t on that graph?
well, it's taking all t values 0 to 1, and then plugging it back and giving you outputs of points x, y
Okay.
from the original function
So why are we seeing what we're seeing?
because x is set to t.
Yeah, x is something. Right. So if x is t and we're graphing from t from 0 to 1, then we're going to see the graph x from 0 to 1, right? So the question was, how do we get to see all of this by graphing it parametrically? So I want to hear some of your. I don't want to hear answers. I want to hear what happened, the process you went through to figure this out. So can anyone articulate what happened as you were trying to solve this problem, starting from the beginning? Or maybe you're still kind of in a state of uncertainty, and you want to share that as well. Alex.
Sure. I'll take a shot.
Okay.
So the way I thought about it was I thought about it as like I needed to shift the graph basically.
Okay.
So it took me a long time, but I was considering like what are the best ways, how do you shift graphs, which would be like, so you can +2, +3, plus y along so x equals t plus 2 will shift the whole graph 2. And so that was just kind of how I was trying to work it out, just by figuring out ways of shifting it, and then I also knew that when you multiply t by something, that like extended the parabola or shortened the parabola. So it's like if you multiply t by 1/2, then the parabola, then the graph only went from 0 to 1/2.
Okay.
And that makes sense because when you t 0 to 1, you're having that. So that was just kind of how I figured it out.
Okay. So it's kind of like a combination of shifts and stretches?
Yeah, pretty
kind
much.
Of? Okay. Someone else? What was your experience solving this? Lauren, you're nodding. Same kind of thing? Or?
Yeah, no, definitely. I struggled with it as well, trying to figure out how to set my bounds. I tried doing the inequality, and it was like, nope, can't read that. So I was like, okay, well, that's out. And then the same thing, I knew that I needed the values in the given interval, and so I found the length of the interval, which was 5, and so I knew that all my x values needed to go from the -2 to 3, which is 5 units long.
Okay.
And then somehow I needed to be able to manipulate my t. When it inputs 0, it'll give me -2.
Okay.
When I input 1, it'll give me 3.
All right, stop right there. So what'd you say there? You said?
I needed to manipulate the t in order for when I input 0, I'll get an output of -2. And then when I input 1, I need to get an output of 3.
Okay, I'm going to pull that nugget out of what you said. And somebody else. Crystal.
So we know that ST varies from 0 to 1. We want our coordinate pairs to vary from -2 to 3.
Okay.
So I would set up an inequality. So 0 is less than 2 is less than 1. And what can I multiply or scale that by to make it a width of 5 units? And then what can I subtract or add to make that interval start at -2 to 3?
So it sounds kind of like Alex, but not a you're using shift and scaling and shifting, but you weren't thinking about it visually. You were thinking about it more mathematically.
You're not scaling and shifting the graph, you're scaling and shifting the interval.
Right. So more numerical shift and yeah. Okay. Other thoughts? Yeah, Michael.
I was trying to get those 2 endpoints, and I couldn't get the whole graph, so this isn't the right way, but I was trying to do kind of how we were graphing the line segments, so I did 1 minus t times -2.
1 minus t times -2.
And then plus t times 3. So I figured when t was 0, then it would just put in -2. And when t was 1, then it would only graph 3. Or it would give out the outputs of 3 for x and -2.
Does it work? Zach, say no?
Well, I don't. It depends on. I guess that is what you're putting in, into the.
That's what I put in for t, the top. instead.
So you said this right here
Put in for what the x coordinate was.
was your x coordinate because this is x, right? And then what did you put here?
I left that. I didn't know what to put there.
Oh, you're a moment from brilliance. You're a moment from brilliance. So what should you put there? What do you want, G? So you want?
Well, since I talked to Zach, like, do you want me to give away this?
Oh, okay. So you someone told you later.
Yeah.
Okay. First of all, so what do you guys think? What's your reaction to this? It's a really cool way to do it. So let's get her done. So is G of t, is that gonna? Let's try it. So let's put this in. So 1 minus t times -2 plus 3t. And then g of t. Okay, so let's graph it. Chelsea.
Does all that same stuff you just put in for T needs to be inside of, or needs to be the input for T?
Why? She wants to take that same stuff and put it as the input for G.
Is that my input now? That's the whole thing makes up the input, not just.
The whole thing makes up the input now.
As T varies from 0 to 1, G of T varies from G of 0 to 1.
Right now.
Yeah, when you have it like that, but we want it to vary from G of -2 to G of G of 3.
And that will be accomplished by?
Using our equations for x as the input of G.
Yeah, so what she said was right now, the y values are going to vary from what to what? G of 0 to G of 1. So we saw before that it was this little thing right here, right? Right, like that. And so now we're getting those same y values, but just over the interval from -2 to 3 in x. So in order to get the y values, the true y values from -2 to 3, not from 0 to 1, we're going to use that thing. Okay, so I kind of introduced this idea to you, and I gave you a couple examples of it, and then I waved my hands and I said, look for ways to use it. Look for ways to use it. So because this is a really powerful thing, and it's so now this is still a third. What was the first way that we saw it? Yeah, so it was from one point to another, right? So we were using this mapping idea to do all the points from one point to another. And then what was the next thing that we saw for us? Remember we showed in class last time? We used it to the same technique of 1 minus t times something plus t times something.
It's two functions, right?
Yeah, so remember we saw the function, right? So when the t value was 0, you had one function, and then as you let t change from 0 to 1, it transformed it into the other function, right? And here's still a third different way. So how would you describe how it's being used here? We got from point to point, from function to function, and what is this?
Restricting your domain.
So this is taking values of t and mapping them to just values, right? Values. So from a value of t, mapping it to a value of x. Okay, so this thing is very versatile. It can be used in many ways. It's a really powerful idea. Okay, let's move on. So how'd this problem go? Was it fun?
Oh yeah.
After and before it was fun, like with the spirals and stuff.
You didn't like 4. No, this is number 5. That's what I'm talking about. Yeah, cool, good. All right, so let's check this out. So we got control 3. Z.
Oh god.
Okay, so if you remember, I think I showed you guys this with the three-dimensional graphs. If you do Control Z, I think it is. Yeah, Control Z. There's some way to do it on PC. Anyone know how to do it on PC? Just so you can get a better image. It's too big. Okay, that's good. Gee whiz. Stop. Okay. There we go. So we want to get something that looks more like what the original image was. How do I do that? So I just want to show more of this thing, right? How do I do that? How might I show it more the image that was given on the page? Yeah, Tori.
Well, the image on the page had more spirals, which means you have to have in the same like height. You need to have more circles that can fit that height.
So was that image was the final version, or the original version after we? Oh, okay, so this is after we make it more dense?
Yeah.
Okay, all right, so we'll start with what we got. So we'll go to the question, how do you make the spiral more dense? So somebody knew, tell me what you're thinking in this process of solving this. Tyler.
I looked at it and I was like, well, we just need it to wrap around more times in
Okay.
the same height. And then with that, I looked at the arguments we have, and we already, reading for the problem setup, you put 2 pi in front of it to make it wrap one time.
Okay.
So then I just you could just put a k in front of that, and then that would scale how many times it wrapped depending on the number you give.
So without the 2 pi, how far would it wrap?
1 radian.
1 radian, right? Less than 1/4 of a circle, right? So good. So he's thinking, 2 pi made it wrap from 1 less than 1/4 all the way around. So I just need to scale it up more. So let's make k. Did anyone make k a slider? So did I show you how to make sliders? Just new sliders? So you can go k equals, and then you just type out slider. And then,
That's all we have to do?
no, that's not going to solve the problem.
Well, I know, but I didn't know that was like how you made a slider.
Yeah, just type in slider. And then,
Is that multiplication or
what now?
parentheses?
It's not multiplication. Now this is going to be defining what the slider does. So the starting value of 0, ending value of, we'll say, 100. Wow, that's impressive, huh? I guess. Okay. And we'll go by ones or something. So starting value of the slider, ending value of the slider, and then, oh no, that's how many steps, sorry. How many steps. So if you want it by 1, then you need to do 100. So if I want the original picture, what do I set k at? 0?
1.
No, wait.
1?
You need to put a k in here. You got
Yeah, I know.
K equals 1 will give you the original.
K equals 1, I'll give us the original, but now I gotta put the k in. Here we go. So we put the k in. And so this should be the exact same graph. It is. And so if we're correct, then what will happen?
That'll increase the spiral 50 times.
Look at that.
That's cool.
Worked. So you can have as many sliders as you want, and they also work nice for turning on and off things, which we'll see in future projects. You can use a slider to like be at different views of something, like view 1, view 2, view 3, and you just move the slider down and it changes the view, whatever view you want, the way you've created it. Okay, cool. Somebody else. So now I think the next thing was making it a cone with linear sides. Somebody new. Carla.
I struggled a lot with that.
Good. That's okay.
I just wanted to multiply
to it. I was
Okay.
like, this isn't working, so let me just try.
Okay.
And I knew I wanted to multiply like the outside of it by something, but I didn't know what. And so I tried like different numbers, and they would just give me like the circle would just be like wider or like thinner and stuff like that. So then I was talking to Crystal, and she was like, and I was like, I'm multiplying by different things and it's not working. And she's like, well, what do you notice about the color? I'm like, well, the width is like varying as you go higher. So she's like, so what do you multiply by something that's varying? And I was like, oh, T.
Right.
So that's how I came up with that.
Okay. So as you go higher, you want the radius to get bigger. So how do you do that?
So you just multiply cosine and sine by
Out in front like this? Other experiences on this one. So if you want to talk about, yeah, Molly.
So how I thought about it was, I got the circle.
Cylinder.
And trying to get it to look more like well, that means like it has to start at 0, 0. And the only way I could be doing that was having it multiplied by t, which at the base is 0. So when you put that in, it causes the point to be at the origin. And then when it increases to like 1 or however large you make it, it will expand out.
Right.
And that's how you multiply t by cosine t. So that it's at 0.
What do the x and y, the cosine and sine represent? Taken together, what is that about?
Say that one more
So when you're looking at the x and y, which are clearly kind of different in terms of their rules than the z rule, cosine and sine for x and y is representing, what is it representing in this? Yeah, circles, right? These are the circles. And so we want those circles to have a larger radius as z increases, right? So this is why multiply by t. Okay, somebody new on part C, so we want this thing to, so was it n? We're going to use n to, how can we inject n now to make this thing flatten up and stretch out? Somebody new. Yeah, go ahead.
Well, I had put in n into all three, into x, y, and z.
So tell me what you did. Let's do it.
I kept the t cosine, but multiplied it by n.
Right, like on the coefficient here?
Yeah, but I did it for x, y, and z.
Okay.
But
And so let's predict. So for those of us who haven't done that, what's going to happen when I change n? Think about this. What's going to happen when I change n? What's that?
It's a little ball.
It's going to expand straight up. What do you think?
And upward too.
And up?
Yeah.
Up and down and up.
Yeah.
Expand in all directions. Up and out. Okay, let's see how that prediction.
So it just like shrinks the whole involved.
Yeah, it does that, but is the cone getting wider?
It's maintaining like the constant.
So it's not really expanding outward, is it? What's happening here?
It's scaling. It's scaling as it increases.
Scaling as it increases.
So it becomes like 2, 3, 4 times larger. While
Yeah,
maintaining
staying
the
in the same dimensions.
So let's just, how about just the z coordinate? So multiplying just the z coordinate by n, what is that doing?
It's kind of flat.
No, I'm saying in where we have it now. Anyway, so let's go on. Is this yours, Sarah? So you want to keep going? Yeah, why don't you keep going? So what happened?
well, then I spoke to Lee afterwards because I was saying, well, it's not showing the same things with the picture ones, and he asked me what the z coordinate does on the graph, and I said, well, it changes the height, and he goes, so the n value just changes. If we put it in the z value, we'll just change the height of it, whereas if we have it in the x, y, it's also going to change the width of the circle.
Okay.
So if we take out the n out of the x and y, then we should get the result that we needed.
So I need n. Let's do n from here. So we'll change n from 0 to 1. How about? Yes? Did it work? All right, so if I get a perfect bird's eye view down the z-axis of this thing, and we change n, what will you see?
Nothing.
People are saying nothing. So the trick to this is getting a perfect bird's eye view. Maybe. Maybe. Not bad. Pretty close. But there's a little angle, right? There's a little angle to it. Okay? And so why is that true? Why don't we see anything changing when n changes from this view?
Doesn't affect the x or the y values.
Okay, and? Doesn't affect x and y values, and?
And it only affects the z value.
Okay.
Because that's the only place we put it. The x and the y coordinates have no n's in it.
X and y coordinates have no n's in it.
So when we change n, there should be no change because that n doesn't even show up in our x or our y coordinate.
Okay.
But when we have n in our z, when we change our n, it's going to affect where it is.
Right, and then how do we tie that to this view? So we just got one more connection to make.
So in this view, we're looking straight down. We're not even looking at our z values, and so we're just looking at the x and the y.
We can't see any distinction between z values. We can only see x and y. So when we change n, it's not going to change anything because the n doesn't affect x and y, right? Cool. And the last one should have been really easy. It's kind of in the past I gave that last area one before you do the kite and the heart. So, but I just left it on there. So hopefully that felt good to have a nice easy one. Yeah.
How do you do it parametrically?
Oh, did anyone figure out how to do it parametrically?
I didn't want
Yeah.
You can't do it. Well,
I thought about. I didn't think about it a long time. I thought about it a little bit, and I didn't get anywhere. So, yeah, I think one line would be impossible, but it's still maybe possible. I just need more time to think about it. So, any comments or questions on the homework? Okay, so I want to talk about. What do I want to talk about? Here's a cool question. This is the path of a caterpillar. Maybe. All right, so here's the path of a caterpillar as it crawls from point A to point B on the wall. You see the path? Well enough. Okay, so I want you to have a discussion at your table. Is this a function? Okay, have a discussion at your table. Go. Is this a function? Go.
Vertical line.
I mean, look, it's it wouldn't look like that.
But we could break it up into parts and say from like the half of it is a function on the left side.
Yeah, that's basically.
We just the left side, but it's not a function as a whole.
It almost looks like a flat image of this 3D movie. I feel like there's like I'm wondering if some of those lines are not actually not overlapping.
Oh, if we're looking at it like.
No, that's used on the wall. Caterpillars on the wall. They don't fly. It's vertical wall.
It's not climbing around a tree.
Right.
There's the word with 3 seconds.
Okay, I want to hear some of your thoughts. Is this a function? What did you think about it? Your table. Talk about your tables. Yeah, Daniel.
Well, what we said was there's no input values. It looks like they just like trace the path of the caterpillar
Okay.
with just height above the ground.
Okay.
There's no input value really. They weren't really checking independent variables and how it affects the height.
So then would you conclude at your table in terms of answering that question? Is it a function? It's not a function because
there's no relationship. The graph doesn't represent a relationship between height and anything else.
the graph doesn't represent a relationship between height and anything else. Okay, so all right, that's a good picture. Does this picture represent a relationship between two quantities?
Just height above the ground.
And position, like horizontally, right? It just doesn't have a scale.
Well, it takes some time to crawl.
What's that? It takes some time to crawl.
Yeah, but it doesn't show time. Like it would be a function if it did.
Yeah, if they had like
If they had it in terms of time, it would be a function. But it's not.
Okay, so this is good. What you're grappling with is you're grappling with the right thing. So this is coming down to when I say, is this a function? Why is there perturbation in the room, right? So why? Why is that question causing conflict, Tyler?
So it looks like a graph that we've all gone through our school careers looking at. That should be like that's a graph.
Okay.
And you know, throughout our school experience, a lot of people say it's not because of something like a vertical line test or something, but they're not actually applying like what's actually being done here. So yeah.
So could this be the graph of two quantities?
it could be.
It could.
Or is it the graph of two quantities? We have a vertical quantity?
Ground isn't a quantity.
Okay. Ground is a quantity.
The horizontal position.
Horizontal position from whatever.
What's Zach, go ahead. Zach, go ahead.
It doesn't say what the quantity is, but the ground does. There is a quantity to it. Like there is a certain distance traveled this way.
Somebody say horizontal position. Horizontal position. So could this be the graph of the height above the ground as a function of horizontal position? Was that the graph of that relationship? Distance above ground as a function of horizontal position or horizontal distance. Say this is the edge of the house or something like this on the house. This is the edge of the house. So distance to the right of the house. Could that be the input quantity such that this would turn out to be the graph? Making eyes, Laura.
Oh, I was just, yeah, I mean, if, making eyes. Yeah.
This be the graph of that relationship of height and distance to the right of the edge of the house. Would this be the graph? Tyler.
Well, you wouldn't have a one-to-one function because at a certain point there, you all of a sudden have 5 different outputs for a single input of horizontal distance from the side.
Okay, so now you're talking about if it's a function or not. So we're just establishing, can this be the graph of these two quantities?
Yes.
Is it the graph of height and horizontal distance?
Yes.
Yes, sure. Now, so yeah, we need that. So when I say, is it a function, what is a function of what, right? What is a function of what? So if we say, is height above the ground a function of horizontal distance from the edge of the house? Yes or no? Why not? Hold up here. Why not? Why is height not a function of horizontal distance from the edge of the house? The class has decided that the height is not a function of horizontal distance from the edge of the house, because this is that graph of those two quantities varying together.
Because we have more than one y for one x.
More than one
Y. More than one value for height.
value for height for every
Horizontal distance.
for every horizontal distance. You have more than we have more than one value for height. We're good? Okay. So now here's the actual question. fireworks on the wall from point A to point B along the path shown. Caterpillar's height above the ground. Is the caterpillar's height a function of the time elapsed since the caterpillar started moving from point A? Go. Talk about that. I'll make it smaller.
This would be because at any given second, like there would be no the caterpillar couldn't be at 2 places at one time.
It would go back to the same height, but it would never go back to the same second. One second.
You wouldn't have the there wouldn't be able to and
It would not look like that.
Yeah, because I'm still visualizing that. So it would be a different. So it feels like it's first 1 second, then 3 seconds. It'll be whatever.
It'll be the same function.
So every input.
Question.
Does the caterpillar ever stop moving, right?
Does the caterpillar ever stop moving? Okay, so does it stop? Okay, so could it stop moving? Could it move backwards on the path and then forwards on the path again? And would that change the question?
Because you just get a horizontal line if it were hyperfunction times.
Well, I'm just saying, like, what if, like, because we have the path and stuff, but like, what if you went like really fast first, then you went like super
It'll be
slow?
like a really steep bar, and then you go.
Well, in the actual graph of like time versus height, it would be, but like if this is a time versus
But that,
height.
yeah, the question is the caterpillar's height above the ground a function of the time of the last?
That's what?
Diagram representing the question. Yes.
I mean, that might be parametrically, and that might be so wide for there's some other.
Okay, what do you think? So how about up here? What you guys talk about? Chris, is height above the ground a function of time elapsed? Chris, what do you think? Not sure. So what is? Do you remember what the kind of the criteria for a function is for a relationship to be a function? Remember what it means for two quantities to have a function relationship? Oh, Chris, do you remember what that was? Doesn't remember. Raymond. What does it mean for two quantities to be in a function relationship? Remember?
Not really.
Okay. Let's see who else. Melissa, you've been more quiet today. Melissa, how about?
Well, they have to have a relationship. Is that what you're getting at?
No, so there's a criteria that has to be met for it to be a function. We're asking, is it a function? So we got to know, what does it mean for two quantities to be a function?
But they have to be some kind of relationship of, I guess.
Okay. Sarah.
For each x value that you put into your function, it can only have one y value.
Okay, so for each input, you can only have one output. So that's what we're holding this question up against, right? For each input, whatever the input is there only one output? So yes or no. What's the input here? Time elapsed. Output is height. So the question we ask is, at every time, time is input, right? For at every time, is there just one height? Yes. Okay.
Well, you can't
You can't be at two different heights at one time.
Right.
You would have to be a multiple of themselves. You don't have that technology.
Yeah, so at any given time, is there only one height that we would measure for the caterpillar at any given time?
There's no time. You have to think of okay, I can't. This is his path.
You're shaking your head,
His
Melissa.
path increases this time.
Well, if we're going time, there, like what we said, he can't be in the same, in multiple places at one time, so there's not one output
If you're looking at just this graph, but they're saying this graph.
This graph is still the path of the caterpillar. Here's the ground. Here's the height.
This graph isn't showing.
This is the path of the caterpillar walking on the wall. Is the caterpillar's height a function of the time since he started walking from point A? Was he only one height for every time? Yeah. All right. What about the vertical line test? This fails the vertical line test.
That's
What's that? Lauren.
If you were to just look at this graph, it's not in terms of the time, like your x-axis is not labeled as your input as time, but if you were to follow all the points on his path, he would be at, time would be 0 at A, and then say you were to move up to the curve, like that would be a different time for there, but you have to follow the time along the graph, not along the axis.
Okay. Are we good? So this curve as a graph, could it be a function? Could it be a function? Top of your tables. Could this curve that I'm showing you be a function? Could it be a function? Talk about it. This curve that I'm showing you.
It could be a parametric function. As I said, the height will be the y value. Some other equation could be the x value, so it could be a parametric.
That's like one of the main things about parametric functions is that you can have multiple y values for
You would technically be
like the circle.
We're just talking about comparing the outputs.
Okay. Anybody come up with something or a response to this? Could that curve be a function? Chelsea says yes. How could it be a function?
If you followed it along like this with your pencil or something, and then you had different times for each time your pencil touched down.
Okay.
Even though it like crosses itself at one point, that was a different time, a different input. Like time 3 was at the same time as time 20. Doesn't mean it's not a function.
So if you're telling me it could be a function, then you need to tell me what? You got to tell me.
Yeah, for every input there's a unique output.
Okay. So.
I don't like this. So.
If you change what you're comparing your points to, like so if you change instead of comparing your height to the horizontal distance, horizontal distance along the wall or whatever, to a different independent variable or input like time, then it is a function.
Could this curve be a function?
No.
Could this curve be a function?
As in its work. Like that picture right there. Right.
Tyler, are you saying yes or no?
Are we taking that curve to be height to the right of the house and height
No.
of the ground?
I'm saying that curve. Yes. Yeah. Sure. Yes. This curve is to the right. This is to the right and distance up. That's the way we get that curve. Horizontal and vertical distance. What's that? How could it be a function?
If you look at it in terms of time,
What time? What?
Okay.
So
It can't be a function.
No. It's just not. If you're talking about yes, it could be a function, then what do you have to specify? Zach.
It can be a function because there are multiple inputs where there's more than one output. So
But you haven't defined the quantities, you guys. You're just saying yes or no. Functions are about an input quantity and an output quantity. This can be a function. This curve can be a function. You've got to figure out what the input would be and what the output would be and define those quantities. Go, do it. It can be a function if you define the right input and output quantities.
So the input would be t value, output.
So maybe like how we're talking about here, where our interval would be some time whenever we have to some kind of beginning. And we get lots of score that is based on that interval, and it says that's why our input would be our interval 0, 1 times x is the horizontal position and y is the vertical
For some given time, you're a certain height and a certain position.
So it's still a function.
So if you're thinking about 1 second, that little dot when you put your pencil there, what do you have? You have height and output. And then if you were like, okay, 1 second, 1, 2, 3, into the earth, what do you have? Height.
Instead of like defining something parametrically, what's it called if you do it just like x equals y? What's that?
Oh, not parametrically, so it's well, there is a name for it. It's like just y is a function of x, meaning?
Yeah.
Yeah, so that's well, no, Cartesian is the plane, right? Cartesian is the plane. XY plane is the Cartesian plane. Yeah, there's
The name for that.
Okay, anyone think they got it? How can we define input and output quantities so that that curve represents a valid function? Laura.
So if we input time since time elapsed since
Time elapsed.
he started moving, the little guy, caterpillar, then the output is a given position and height. It's a point.
How are you defining position?
It's the horizontal distance and height.
But
Coordinate pair. So it, like you're given
coordinate pair.
Yeah.
We need to get this curve, right? We need to get this curve.
So you're given the horizontal and the height to get an overall position. The x and the y.
Okay, but that's the output. So when you said you're given, that sounds like input.
Okay, you're getting out of it.
Right.
Yeah.
So time elapsed is our input, and then position is our output. To define position, it's going to be ordered pair. Is there just one ordered pair, x and y, for every time?
Yes.
How do we define a function like this? Parametrically. Parametrically, right? It's a parametric function. That's a parametric function. Position is a function of time. That's a function where t goes in and an ordered pair comes out, and there's just one position for every time. And that's the curve that you get. Okay, so this is to introduce a discussion about what's called shape thinking. So how do students answer this question? The original question, you give them this question, and you give them this graph, and what do students say? They say, yes, it is a function, height is a function of time, or no, it's not. They say it's no because it doesn't pass the vertical line test. It doesn't pass the vertical line test, okay? So, which is, that's errant because that's not the graph of these two quantities, right? This is not the graph of the two quantities, right? So that's an example of what's called shape thinking, okay? And so shape thinking, as you guys do, as you do your internships and student teachings, you'll become very aware as we talk about shape thinking in your students, the way they respond to questions. So in general, what have you know about this before? So how How are they thinking about it when they apply the vertical line test to this question to answer no, it's not a function? How is that shape thinking? What are they thinking about? Yeah, Michael.
Are you saying like they're automatically assuming that the graph represents what the question is asking?
Right. Okay. Yeah. Other thoughts about that? So yeah.
It's kind of like when we were changing our axes with the ellipse and the circle, where you're like, so is this an ellipse?
Right. Okay, that's a good example. So it looked like an ellipse, but it was a circle, right? It was a circle. So that's shape thinking. Yeah. So they're taking visual clues and shallow understanding to make conclusions. That's what we mean by shape thinking. There's all kinds of ways that this shows up. Okay. So here's another example. Which has a greater slope? Which has a greater slope? Which line has a greater slope? The one on the right, right?
No.
Okay. How do you know which has a greater slope? Which line has the greater slope? The blue line on the left has a greater constant rate of change than the one on the right. It's just a math. Why does the one on the right look steeper? I've messed with the scales, right? I messed with the scales. So students who use shape thinking, oh, the one on the right has a greater slope, right? But truly, this has a greater slope. So slope can only mean constant rate of change. It can't mean steepness for this very reason. Because the steeper line has the lesser slope. So slope can only mean rate of change. It's a number, right? It's number, it's not. And so if you take the visual cue, you get it wrong. So that's an example of shape thinking. Here's another one. Ready? Here we go. All right, so now we want a graph starting from where he started. He started there, right? He started there. So can you quickly sketch the graph of this relationship? His distance to the right of his starting point as a function of his time since he left this position. So see if you can sketch that graph. Sketch his distance to the right of his starting point, or to the right this way in the pipe. Compared to time since he left that spot. Okay? Is the task clear? And so you just do it for one pass from this left side of the pipe to the right side of the pipe. Just do that first pass. And then after you're done, I want you to sketch what you think a student would sketch for this, maybe doing this exercise. What might a student sketch for this? So I want to see your graphs here.
That was the time goes down. Your distance goes down. Time goes over.
Yeah, so the outputs are equal because when it's coming Like
Yeah.
some of the time he's going downward
That's
more
where it
than
starts.
over than he
It's
is.
just information that starts
Right. Well,
Here it goes again. We'll see him again. Here we go. Here he goes.
So when he's at the bottom,
So what happens?
So show me your graph.
Just initially,
As soon as he starts increasing, he's going to start.
the amount of time he's taking is actually going down. He's going less horizontal.
that's what I said.
Right.
So he's going vertical distance a lot.
Because this is saying that he's moving really fast on the road.
That time
And it's slow.
Yeah. Okay, you guys got the idea.
Yeah.
So there are a lot of
That's what you first do. More time is passing as he's going down the road. And then, like, right here is where he's right in the middle, so it's moving here. He's like traveling
Distance is increasing.
Okay, so I hate to interrupt you. You got some rich discussions going on here. There are nuances in the graph, and all of you correctly did something like this. Okay, for him to get started. But what if students use shaped thinking to create this graph? Oh, it's just going to be right. So this example of shaped thinking, they're seeing something visual. They're taking a cue from what they see. Oh, that's what the graph will look like. It'll look like the half pipe. Right? Or this is the skateboarder skating down the graph. In the background. Okay, so let's have a discussion about. So this then comes into where is it? There it is. So this is going to play into your problem solving, creating visuals. Okay, and so let's talk about what you guys think are some characteristics or some examples of good mathematical solutions in terms of building visuals in GC versus using shape thinking to build visuals. So this is something you guys are going to fight too. Okay, as you're going after creating these kind of harder visuals, what would a good mathematical solution look like versus a shape thinking kind of solution look like in your process of building a GC animation? So let's just open it up and have you guys tell me what you think. Any thoughts? Tyler.
With good mathematical solutions, you're understanding which quantities are changing and how they're related to each other.
Understanding So okay, that's good. Maybe let me frame the situation a little differently. It's like if you were to look at somebody else's command lines in a GC file that they built a GC file of an animation, and you're looking at their command lines, what would you see that would be would indicate good mathematical solution versus shape thinking? Yeah, but then also the process. Okay, so then also the process of how it's being built. But yeah, so if you were looking at someone's GC file, what would demonstrate that they had an understanding of which quantities are changing and how they're related? What would show that? Versus shape thinking, you would see that maybe they don't have that. Makes sense?
I think with good mathematical solutions, they have like parameters defined.
Okay.
And they can come back and use those parameters.
Good. Okay.
Whereas with like shape thinking, they're just trying to get it to look a certain way, and so they'll just throw numbers around and try and get it to look how they want it to.
So what'd you say there?
So with good mathematical things, there'll be parameters, whereas with shape thinking, they're looking at the graph and trying to get it the way they want it to look, so they'll just throw numbers around.
Okay, so kind of random numbers to create images.
Yeah.
So seemingly random. Okay, other thoughts on what a good mathematical solution would look like in a GC file and what shape thinking would look like? Yeah,
Like a concise number of commands so that they're thinking to think about each one before they say, oh, if what is this absolute value instead of them they have absolute value but they're like, oh, I just have x and negative y equals x.
Okay.
So they could have done 2 command lines to do that.
All right, so you're talking about efficiency.
Yeah.
Efficiency in.
I needed the sword.
That's okay. Yeah, so efficiency in command lines, as opposed to what would, instead of efficiency, what might building a GC file look like if it wasn't efficient? Disorganized? Cluttered?
Just an excessive number.
Yeah, more command lines. Yeah, and this is, so
The first
extra lines, disorganized. Other thoughts? What would be a good mathematical solution or shape thinking would be evident in creating a GC file to make an animation? Other ideas?
shape thinking, you have like multiple like functions defined that could have been defined by like one function. Like,
Okay. So that goes with the efficiency and the extra lines. Yeah, that's good. Definitely good. Okay, so for time's sake, I expected to start this discussion a little earlier. For time's sake, I'll just show you what I've had from the past and see. You've got some of them, definitely. So I have is developed based on understanding and problem solving. Trial and error till the image looks right. Okay, so you can just keep trying stuff until the image looks right. It's clear how it relates to the original question and givens. No seeming connection without some kind of explanation. So that person would have to be there sitting next to you to explain how it what they did relates to the problem, the original problem. Whereas if you read it, it's like, oh, of course, that's how it relates to that original problem. Can be generalized to solve many similar problems easily. This is really important. Shape thinking must be recreated every time the inputs change. So you got to redo it every time the inputs change. Accomplishes the task with the least parts possible. You guys talk about it. And then I'm calling this other thing the tumor approach. So you've got something that seems to work for part of it. Well, now you have to append it, and so what do? You add something new. And then you keep adding something new, and keep adding something new. And so this is where, instead of thinking it all the way through from the beginning, you're just doing it in chunks, and you just keep adding things on. And this will happen to you. It happens to everyone. Okay. So I was going to have you remember the kite string.
Yeah. Oh, I'm glad you let us use it.
So I wanted to look at. Can you read that? Is that big enough? So how does these two ways of doing the kite string reflect these things above? I'm going to change the. How do those two different ways of doing the kite string relate to these things about good problem solving and shape thinking? So here's one way to graph that kite string. Here's another way to graph that kite string. How do you see good mathematical thinking coming through and shape thinking coming through? Yeah, Alfredo.
I think the second one is more shape thinking. It's kind of like the same format we used for the first line graph.
Okay.
So they just took the 2 points that and the line, they just plugged it into that format.
Mm-hmm.
Whereas in the first one, they actually thought it through and came up with something new.
Okay. Agree? Disagree? Carla? Kind of shook your head?
I don't know. I feel like in the the first one, you're gonna have to define the line, like define T again. Whereas in the second one, you're just changing the two, like the points.
Okay, Molly.
I think that the first one was a very specific one, whereas the second one, just change the points that and it'll move the.
So, can be generalized to solve many similar problems easily. First or second? Second, right? Second. Any last comment before we take off? What's that?
There's just less junk in the second one, so it's these parts, I guess you can.
Yeah, so reading this, it would take you a while to figure out that this would start at where? It's going to start at -2, 0, and end at 0, 3. So you could do the math, but to an outside viewer, that's not showing it as well, or not showing it so explicitly. Okay, there is a short assignment for Thursday. It's creating a GC file. I was going to talk about some grading issues, but we'll do that next on Thursday. Okay, and then the next critical précis will be a week from Thursday. And I will give you some time back on another day. Sorry for keeping you late.
We seem here.
She was.
Those two submissions,
Yeah, we didn't know who that was.
Oh, it's true. Yeah, 'cause you're
Yeah.